This is an RNZ podcast.
They say life is stranger than fiction.
One of the research projects we do in my group is to make bulletproof or bullet-resistant materials. And so we've actually been thinking about how we could deform the shape of a bullet coming in at very high speeds.
But sometimes what we see in movies or read in books is so incredible that it obviously couldn't be possible. Or could it?
Normally, if you're thinking something like your salt at home, you'd expect to be heating that up to hundreds or thousands of degrees before you get it to start melting. But these ionic liquids are melted, they're liquids at room temperature.
I'm Brian Crump and welcome to Sci Fi, Sci Fact. This is a podcast where we take science fiction's strangest ideas, weirdest elements, and most unfeasible plot drivers and explore if they actually could happen. Maybe they already have. And in every episode, we bring in a scientist from New Zealand's McDiarmid Institute to explain the theories behind some of fiction's more fantastic flights of fancy. If any theory exists.
It's Cuendillar.
I thought that hard stone couldn't be scratched. That nothing, not even the one power, could break it.
So did I.
What does it mean?
That this wasn't the last battle. I fear it was the first.
Tonight's fiction is based on the Wheel of Time series, written by Robert Jordan, and a particular material from that Wheel of Time series called Cuendillar. Now, this substance, apparently, when you apply force to it, it doesn't break, it just gets stronger. Sounds like the old railway china, actually. And here to discuss what's plausible about it, and maybe implausible, is Dr. Matt Cowan, Associate Investigator with the McDiarmid Institute, and a Senior Lecturer in Engineering at Canterbury University. Kia ora, Matt.
Kia ora, Brian. Great to be here tonight.
Are you a Robert Jordan fan?
I love Robert Jordan. That was my first fantasy book series I read while growing up. So I started about age 9, age 10, and finished up around when I was 30.
So what's the basic gist of the Wheel of Time series?
The story is the journey of sort of this young group of people, and there's been a prophecy that so one of them will become the dragon and face down the Dark One and save the existence. And the whole theme of the Wheel of Time is this idea that ages come and go, and so history is going to repeat itself over and over again with variations of this battle against evil. And the series sort of takes you through these young people's experience leading that battle or being the leaders of it. What happened was the original author, Robert Jordan, died with 3 books still to go. And he was talked down shortly before he died from this plan of having his hard drives destroyed and leaving the story unfinished. And instead what happened was the story got passed on to another emerging author at the time, Brandon Sanderson, and he finished off the last 3 books and really put his own mark on those last 3.
You reckon he hit the spot?
He did a pretty good job. I can't imagine how difficult it would be to take over someone's epic universe and try and finish it off with full credit to them. So I think he did a great job.
Within the Wheel of Time narrative, how important is this substance Cuendillar?
So the Cuendillar, funnily enough, I call it calendar in my head, or heartstone. Easy to pronounce.
That's how it's spelt. It looks more like Cuendillar, not Cuendillar, but that's the way they say it. I assume, how come we know how they say it? Does he say in the book? Is there a pronunciation guide in the book? Or is this based on how they say it in the TV series?
There's a pronunciation guide. So he was a very detailed man, and he put together sort of this index at the back of his book, or the glossary, and with all the pronunciations and notes on how the times and the dates all worked in that universe and everything. So he had a universe inside his head.
Right,
of
so
Robert Jordan.
Cuendillar is how you say it. And as I said in my introduction, you try to break it, it just comes stronger. Is that right?
Absolutely, yeah. So the way they use it in the book, or the kind of key role it plays in the book, is that the seals on the Dark One's prison are made out of this Cuendillar. And so the idea is, okay, they've locked up the Dark One at some point in history, and the seals they've put on his prison so that he can't escape are made of this unbreakable substance. And so the idea being, well, if the lock's unbreakable, how's he ever going to get out of his prison?
And the more he tries to escape, the more he shakes the bars, applies force to the bars, the stronger the bars become?
That's what you'd expect. But they make it clear in the book that although this Cuendillar can't be destroyed by any kind of force, like you say, any force against it just makes it stronger. It seems like this Dark One's influence weakens the Cuendillar and makes it brittle enough that it can be easily physically broken. I think that's one of the sort of the first hints about what this Cuendillar might be made out of if we were to look at it at the chemistry from our own world.
Okay, before we go to that particular question, I want to ask you a bit about what happens when we... Well, actually, isn't there a difference between force and energy?
Yeah, well, we could think about force being like a physical kind of force, like you're hitting something. So you're putting your momentum energy into the object, or you could think about energy being put in other ways, so through light, or most commonly, the way I would think about it would be heat.
And is Cuendillar also, does it get strong if you try to heat it up? You can't melt it?
That's the impression it gives in the book. Definitely, yes.
So what would happen? Say I've got a cup in my hand. Now, I mentioned railway china, and this looks like a reasonably solid piece of china. You can hear it there as I hit it with my knuckles. It's pretty solid. But if I threw it from a great height, in other words, I used gravity to apply force to it as it hit the ground, and the ground was pretty solid, like some concrete, it would shatter. And wouldn't really anything, any substance we know, it's going to have its limits where it can't hold itself together. There'll be a force that will break it?
So far as we know, yeah. So if we think about what kind of objects would you drop from your tower that would hit this concrete and still be pretty much the same shape as they were before, and you might think like a metal might work like that. So you could drop this chunk of metal off, and it would you wouldn't expect it to dramatically change its shape from that kind of impact. But if you're thinking about something hard and brittle like your teacup, then you're going to fracture that into a lot of little pieces. And I think that's kind of one of the hints at what this calendar could be made of.
But even if if I dropped a metal ball from a great height, okay, the first time it lands on something solid, it might keep its shape. Maybe the second, maybe the third, maybe the 1,000th time it still would. But ever so slowly, every time it hits the ground, a bit of it's going to be broken off, isn't it? And eventually, won't it weather or erode and maybe at one point shatter, or just eventually break up into little pieces and no longer be that piece of metal that I had before?
That's a really interesting question. So I've been thinking about this because one of the research projects we do in my group is to make bulletproof or bullet-resistant materials, and so we've actually been thinking about how we could deform the shape of a bullet coming in at very high speeds. And so there's kind of two questions there. And so one is, if we drop the ball or put in the bullet at a very great speed onto this hard surface, then what we might see is the energy going into the metal material and having it reshape. So instead of having a ball we're dropping from a great height, we end up with a pancake because we've basically melted it on its when it's hit the ground, and it's been able to change its shape. And then there's the other idea of being able to chip away and chip off a little bit of it with kind of every strike and every impact. And I think there's two different kind of things that are happening there. One is that melting kind of, and then the other one is this idea that we're breaking the chemical bond or the bonds that exist between the pieces of metal, and we're creating a new surface. We're splitting away those connecting bonds between the metal and sort of the bulk of the metal, and then changing those bonds to whatever they are at the surface, whether they're an oxide or something else that's reacted with the atmosphere.
But now it's interesting you talked about something becoming a pancake when it lands. Is that because if it lands with sufficient force, the heat generated by the impact will melt it? Is that what you mean, caused by the friction of the impact?
Yeah, so you can imagine all that gravity potential energy. It's coming down, it's turning into momentum energy. And then when it hits the ground and stops, that energy doesn't disappear. And what will happen is that energy is transformed to heat. You see it quite often with people playing squash. They'll warm up their squash ball by smashing against the ground a whole lot of times to get it nice and warm so that rubber will start bouncing around rather than dying on impact.
Why is that? Why does warmer rubber bounce better? I would have thought it'd be softer. It would be softer and it would bounce worse. But I know, I've done this. I've warmed up for a squash game and you whack it against the wall. It's the only thing I'm good at in squash, really. Because, it doesn't matter whether you win or not. You just got to whack it as hard as you can. And it bounces better. But why is that?
Gosh, I don't know.
Oh, Matt, you're an engineer.
I know. I'm letting you down.
So, but we can be confident that it's the warmer the rubber, the better it bounces. We can be confident of that. Right. Okay.
Well, I've seen it. You've done the experiment.
Yeah,
I've done the experiment.
You've done the experiment. Yep. Okay. Well, but what is happening? Well, actually, when we talk about things that can withstand quite a lot of force before breaking, what is it holds them together? Because Matt, that we're mostly nothing, aren't we? Everything is mostly nothing. So why is it that some things hold together that are mostly made of nothing better than other things that are mostly made of nothing?
That's a really interesting question. When I think about it, I think about metals versus ionic compounds. So with metals, what we see are that we've got our atoms that are made up of our nuclei, which are our positively charged parts, and then we've got our electrons kind of floating around those. And with metals, how you could imagine that is this sort of sea of mobile electrons all floating around all over the place. And within that sea, we've got islands of the nuclei. And what we could imagine is that, well, it doesn't really matter where these islands are in the sea. They're always going to be surrounded by the sea of electrons, so they're always going to be relatively stable. And so they can move around, and that's kind of why metals are malleable, more malleable than you would expect from something crystalline. And then we've got ionic compounds, so things like salts, for example. So just your classic table salt. And if you get one of those chunks, you can easily grind it up and make smaller chunks of your salt.
Yeah.
And so salt is an ionic compound. And so what we've got there is the atoms are arranged in this very fixed and rigid structure. So for salt, we've got alternating chlorine and sodium ions in all directions. And that's what, in one way, salt is incredibly stable because those bonds between the sodium and the chlorine are ionic, and they have a lot of energy in them, or they've given up a lot of energy to reach that state. So they're really, really stable. But what that comes with is that they can be shattered relatively easily. So you can imagine if you shift that arrangement by just one, like a giant puzzle, you just shift it by one arrangement, then suddenly you've got sodium beside sodium and chlorine beside chlorine, and they don't like each other, and so they're likely to shatter apart at that point.
There's another thing you can do with salt quite easily. You can dissolve it. You can add water, and that breaks it down too, doesn't it?
Correct. So in that case, what we're seeing is the idea that we've got an even lower energy state if we surround all our sodium ions and all our chlorine ions with water and put them into this water, which is acting as a solvent to dissolve everything. And so whenever we're thinking about a chemical change happening or some sort of physical change happening, what we're thinking about, there's got to be some sort of driving force. So we're ending up in a lower energy state than what we started with.
And does that apply whether you're dissolving something, heating it up, or hitting it, trying to chip something off? All those that applies to all three of those things.
We're always moving towards a lower energy state for whatever the conditions are.
Entropy.
Entropy is one of the factors.
Yeah,
absolutely.
We're always
so if you think
everything wants to eventually spread out until there's even distribution, and once that happens, that's the end of everything, the end of time.
The end of time. Well, yeah, that would be the end of the wheel of time as well. And it's like calendar is the one exception to that rule.
Okay, then, Matt. So, as far as I understand, every element, every substance will break down if you apply some sort of energy to it, whether it's physical force or heating or, I just mixed my physical terms up there. Sorry about that. But I think you know what I'm getting at. Yet, Cuendillar doesn't. Now, that's not possible in our world, is it?
I don't think so, unless there's something I don't know about physics. So you're exactly right with this idea of entropy. Because I imagine, okay, if I take some solid ice and I put heat energy into my solid ice, then the molecules are all going to get further apart and they're going to melt and become liquid water. And then if I keep putting energy in, then those molecules are going to come further apart again. And I'm going to create steam or water vapor or water gas, if you like. And so that whole system is being driven by entropy, which is if we're putting in energy, then the molecules want to spread out and drift apart, so they can be arranged in a whole lot of different formations compared to what they could have been arranged in before.
What might be happening then in this imaginary world that is kind of plausible, that could explain how Cuendillar works, apart from just magic?
So I'm thinking there's two parts to this Cuendillar material. One is that I think it has a negative entropy coefficient rather than everything else I know about, which has a positive entropy coefficient. So Cuendillar seems to become more stable if you put more energy into it. So that you can imagine heating it up and it becoming more solid, if you like, which seems kind of crazy to me. And then the other factor on it must be that Cuendillar is a really stable compound. So if we think about what normally happens if we put energy into something, another thing that can happen, apart from this phase change, is that we would expect it to burn, maybe. So, put energy into a piece of paper, you'd expect it to burn.
It starts to oxidize. It reacts with the oxygen, combusts, and that's the end of the paper.
Absolutely. So you're starting to make carbon dioxide and water from the carbon and the hydrogen in your paper. And
a fair thing. We're the same, aren't we? If you put enough heat, we'll react with the oxygen around us and burn up too, won't we?
Absolutely. It's that old saying, give a man a fire and he'll be warm for an evening. And if you set a man on fire, he'll be warm for the rest of his life.
Man, I haven't heard that one before. You real wits there at the Canterbury University Engineering Department.
It's a Terry Pratchett special. I can't claim
Is it?
Credit for that.
Terry Pratchett. Now that's another rich vein of sci-fi, sci fact right there. But we're talking right now about Robert Jordan and his Wheel of Time series of books. The favourite of my guest, Dr. Matt Cowan from the McDiarmid Institute, Associate Investigator, also teaches engineering at Canterbury University. And the substance Cuendillar, which gets more solid, stronger, as you apply force to it. It doesn't shatter, it doesn't melt, it doesn't combust, doesn't do any of those things. And that doesn't make sense. Right, Matt? But you were on the verge of maybe explaining how it could make sense in another parallel universe?
Yeah, so I'm looking for clues around what Cuendillar could be made of or how it could possibly work. And because we know that it from the books that it doesn't burn, it doesn't become these lower energy molecules when it's exposed to a lot of heat energy. What we can conclude from that is that it is an incredibly stable compound. So as chemists, we'd refer to that as having a very high heat of formation. So it's given out a lot of energy when it was initially formed.
Now, I'm thinking right now of something like a noble gas. Say helium, which is really stable, right? So imagine a world in which, I don't know, for some reason, all other things being equal, helium exists not as a gas but as a solid. But it's really, really stable. And then you can compress it and keep compressing it, and it just, I mean, in the imaginary world of Robert Jordan, the technology hasn't reached the point where it can put it under so much pressure that it begins to, I don't know, disintegrate. In this particular universe where helium is a solid at room temperature, how does that sound as a theory?
That sounds like a cool theory. The part I get you to explain next is how come the helium is bonding to itself, even though, because we know it's a solid, so the helium's becoming really close together. So you've got to explain to me next how helium bonds to itself, but doesn't want to bond with anything else.
Well, helium doesn't want to bond with things as a gas, does it? Why would it be different as a solid?
So that's actually probably why it's a gas, because it won't even bond with itself, and so it will prefer to be all the individual helium atoms will prefer to be by themselves rather than getting close enough together to form a liquid or form a solid.
Because I was going to ask you next, why are all the noble gases gases?
There you go. You've answered your own question already.
There's another thing I was thinking of. There are a couple of lines of inquiry here, Matt. One is, what about the process of smelting? What about the process of, you get your iron ore and then you put some carbon in and you have steel, and isn't that something that's stronger than, comes out stronger than what you put in? And you applied heat to it and you made it stronger. Isn't that a little bit the process of smelting? A little bit what happens with Cuendillar? Just a little bit?
That's really interesting. So in the books, Cuendillar is actually made from iron. So they do something to it with what they call the one power, this mystic force. And then they change iron objects into Cuendillar, and that's how they produce it. Beyond that, I have to admit that I don't know much about smelting and how it works and the chemistries involved there.
The other thing I was thinking of was carbon, because when we apply sufficient force to carbon, and this can be an extraordinary amount of force, it becomes a diamond. And that's really solid, isn't it?
Mm-hmm.
And Matt, why is it that carbon does that? Because, carbon can also be something which, what is it, graphite in the pencil? You can use it you can rub it off on a piece of paper and you can write things with it. But if you apply force to it, you can turn it into a diamond. What's going on there?
Yeah, very cool idea here. So what we would say is that those are different allotropes of carbon. And so they're different ways to arrange the carbon atoms. But without, we can make something purely of carbon, and we can arrange those carbon atoms inside that substance in a whole lot of different ways. And so what you're saying about transforming carbon into a diamond, what you're doing there is the same idea that we've looked at before, which is the idea that under those conditions, these high temperature, high pressure conditions, what we're seeing is that the diamond form is actually the most stable form of carbon. And likewise, under other conditions, you might end up forming graphite and having graphite as the most stable form of carbon, or coal as the most stable form of carbon. What you'll find in every case is that you could take all those types of carbon and you could set them on fire and they would still release around about the same amount of heat. So the difference in energy of the diamond or the graphite or the coal is pretty relatively small compared to the amount of energy they would release when they burned.
However, if you want to set some coal on fire, you don't need that much heat. But setting a diamond on fire, you need an extraordinary amount of heat, don't you?
No, you don't. So
really?
There was a rich. I remember being told about this as an undergrad, and I can't remember the guy's name, but there was quite a rich amateur chemist or scientist back in the day, and he would travel around and he would show that you could set fire to diamonds as easily as you could set fire to coal.
I had no idea. All that money going up in smoke.
Yes.
I really thought diamonds were, they could withstand that kind of stuff. I mean, I was thinking that in order to make a diamond from coal, you'd have to, when you apply pressure, you'd have to make sure there's no oxygen around, or else it will react with the oxygen and form CO2 or carbon monoxide, and that would be the end of the carbon. But if there's no oxygen, enough pressure, it would become a diamond, wouldn't it?
Correct. Yeah. So you've hit on the key point, which is if there's no oxygen around, it can't react with the oxygen and oxidize and become carbon dioxide.
It's a little bit close to Cuendillar, but still miles off, really, because in the Wheel of Time series, this Cuendillar is people trying to that room temperature. There's oxygen everywhere. They can apply heat or force, and it doesn't seem to change it. Whereas if we were going to make a diamond out of carbon, we've got to make sure there's no oxygen there, and it's probably deep underground with a huge amount of earth above it before it will become a diamond. So it's not quite there. It doesn't really sound to me like there's anything in our world that really comes close to Robert Jordan's creation.
No, nothing. We've found different aspects of it, but we haven't found the substance itself.
Do you think we ever will? Doesn't sound like it to me, because we know the elements at the bottom of the periodic table, the ones with single-digit numbers, well, we know what they are, and you've already ruled out helium because you pointed out to me that it's a gas because it doesn't bond with itself. That's why it's a gas, and I didn't know that until this conversation. But anything that has something we haven't discovered on the periodic table, they're going to be really unstable, aren't they? Because they've got such a massive atomic number.
Correct. Yeah. So how we would think of those is that they have a lot of energy in them, and so they're more likely to be very reactive or even self-reactive and break down on a nuclear level.
But you did say something at the start of this interview, Matt. You said that the way it can be destroyed could give us a clue as to what it is. Now, just remind me of that, Matt. Even if it's not plausible, I'd still like to know.
Okay, so in the books, what happens is the Dark One is putting out his influence into these seals on his prison. And what they observe is that the Cuendillar becomes more and more brittle as the Dark One puts his influence into it. And so what that's suggesting to me is that we've got some sort of metal-ish kind of substance that has a very, very high heat of formation, so it's got a very low energy. And the Dark One's influence is maybe not destroying the Cuendillar, because nothing can put force into it to destroy it. But maybe what he's doing there is crystallizing the pieces of Cuendillar, so that we're moving from this sort of robust metallic material into a more ionic one that's then very hard and very susceptible to cracking, just like your teacup and your saucer that you've got in the studio.
And what's the substance that exists in our world that would most likely do that?
Oh, that's a great question. I'm thinking of ionic substances like iron sulfate, since it's made from iron. Iron sulfate has a very low or very high heat of formation, so it's let out a lot of energy when it got formed. And what the missing link for me is that's a very strongly ionic compound. how do we make that into a more malleable metallic kind of compound? There's some materials that are kind of like that in a way. So they're called ionic liquids. And these ionic liquids, they have an anion and a cation, so something negatively charged and something positively charged, just like a salt would be. But these ionic liquids melt at room temperature, so they end up being a liquid at room temperature. Normally, if you're thinking something like your salt at home, you'd expect to be heating that up to hundreds or thousands of degrees before you get it to start melting. But these ionic liquids are melted at, they're liquids at room temperature. And so we're kind of looking for something somewhere in between this really hard aluminium sulfate that is a hard solid at room temperature, and these ionic liquids that are these soft liquids. We're looking for some sort of metallic ionic species, somewhere in the middle, I think.
Could we maybe one day find a recipe for this?
Gosh, that's a cool idea, Brian. I don't know. I don't have one, but if I come up with one, I'll let you know.
There's one other substance that is kind of not indestructible, but can take a long time to break down that we haven't discussed, and that's plastic. Do you think there's anything plastic about Cuendillar?
Cuendillar reminds me a lot of plastic. So it's this incredibly useful, long-lasting material. In the books, they'll have sailors going out, and the sailors will be fishing, and they'll drag up some Cuendillar cutlery or teacups or some other objects in their nets, and suddenly become rich because they can sell the substance, sell these materials off. And for good reason. They're unbreakable, extremely light. What you would give, to have in the books a sword made out of Cuendillar or armor or something like that. So unbreakable swords and armor. And plastic's very similar to that. So for us as humans, we use plastic for so many different things. It's in our clothes, it's in our carpets, our cell phones, our cars. The chair in my office is made out of plastic. We use it for
the arms, plastic. Yep.
Yeah, packaging food. Allowing us to distribute food around the globe. Carrying water, carrying milk. It's an incredible substance, plastic, and we use a lot of it. But as you're right, it takes a long time to break down in the environment. So it's kind of like Cuendillar in that way. And that gives us a really tricky question to deal with for our own world, which is, what do we do with all this amazing material, this plastic material, when we can't easily recycle and reshape it into other objects?
And that's an issue of plastic. I mean, you can recycle it a few times, but isn't one of the issues is the more we recycle, the more brittle it becomes, which sounds a little bit like what the Dark One does to Cuendillar.
Wow, interesting comparison there, Brian. That's really insightful. That is one of the flaws in our plastic recycling, or one of the methods. So with thermoplastics, what we can do is we can heat them up and melt them, and then recast them into a different shape. But absolutely, we lose some of the structural integrity when we do that. There's another process that's emerged recently, which has been pioneered by the Saudi Basic Industries Corporation. They have this process called a true circle process. And what they do there is they take the plastic and then they break it down with heat and a specific catalyst. And they break it back down into the monomer materials that got used to make the plastic in the first place. And then they can feed those monomers back into their plastic making process and create really high quality plastic once again.
Sounds brilliant. What's the catch?
The catch is the catch with everything, which is nothing comes for free, and the energy required to do that is always going to be a cost.
And at the moment, maybe it's maybe it's a lot of energy that's required to melt it and to break it down. I'm also wondering if there might be some waste byproducts from using this particular catalyst. Do you know, Matt?
I can't imagine that the conversion is 100%. So I imagine there are some byproducts, and whether those can get recycled back into the process or not, I'm not sure.
So what we've reached, I think, is a conclusion that Cuendillar doesn't exist in our world, but there are aspects of some substances that are related to it, perhaps.
Yeah, it's a dream, and sometimes you've got to have a dream to start taking steps towards it. Whether it's physically possible ever to have a substance like Cuendillar, I don't know. And if we can find a way to make it real, then hopefully we can also come up with a way to recycle it as well.
Thanks for listening to this episode of Sci Fi, Sci Fact, hosted by me, Brian Crump, produced by Andrew Robinson, and of course the whole thing is made possible by the incredible knowledge of those brilliant scientists at the McDiarmid Institute. You can find more episodes of Sci Fi, Sci Fact on the RNZ Podcasts page. RNZ's podcasts are also available on Apple Podcasts, Spotify and iHeartRadio, or just about anywhere where you find your podcasts. And if you don't want to miss new episodes, well, make sure you follow us.